Hi, today we're going to look at a past paper for Level 3 Calculus, and this is the standard 91577, which is the complex numbers external paper, and this is the paper from 2019. I'm going to take you through the worked solutions. So question 1a, we're solving this equation. We need to give it in a particular form like this, which is your standard complex number arrangement, and we're just going to apply the quadratic formula for this. So we have that x equals b plus or minus b plus or minus the square root of b squared minus 4ac all over 2a, and that's what this looks like with the numbers put in from that equation, and then work through simplifying that. So we get a square root of negative 12 over here, and then sort out what that means. So 4 divided by 2 gives us the 2 just here, and then if we were to put that 2 inside of the square root, it would become the 4, because we'd have to square it, so that becomes 12 over 4, giving us the 3 there, and of course it was negative to begin with. Now we tidy up that square root of negative 3, which would be the same as negative 3 times by negative 1, so then we have the root 3 times by the root of negative 1, which is I. For part B, the clue here is that we're told what the remainder is. The remainder is 38 when this polynomial is divided by x minus 3. Now to do this, we're using the remainder theorem. So we put in 3 into our polynomial. We get that from this part here. So if we're dividing by x minus 3, then we use the root that would come from that, which would be 3, if that did divide exactly. So put the 3 into that polynomial, and those values come out like this. So we're just substituting 3 in, and we're told that when we do that, the remainder is 38. So when we substitute in the 3, that thing will equal 38. We go through and solve that. We get p equals 5. For part C, we've got complex numbers u and v that we're given there. We've got a q in here. This is quite common with the questions that are worth more than achieved, is they'll put some algebraic values in there, so you can't just do it on the calculator. So here we've got the modulus of u divided by v is equal to 13. So let's work through what that means. So the modulus of u divided by v is the same as the modulus of u divided by the modulus of v, and for each of those we can work out what they would be. So for u, we're talking about the square root of q squared plus 4, and for v, it's the square root of 1 plus 4, just by using the modulus, how we know to get modulus from these two complex numbers. Then we set that equal to 13, as was given to us in the question, and we work through solving that. So if we square both sides, we get this. Work through solving that, we get q squared equals 841. So q must be plus or minus 29. Don't forget the plus or minus there. Since we're finding all the possible values of q, don't just take the positive square root. Okay, part D, we've got an equation and one of the roots. Now this is a cubic equation. That means we'll have 3 roots altogether. So we need to find the other 2 solutions. Now the first one's pretty easy. If you're told one root that's complex, the first root that you can find straight away is the conjugate, because if you've got a complex root, its conjugate is also a root. Now we can use them as factors by doing z minus each of those roots. Work out what that would be, so expand that out and work through simplifying it. So we end up with z squared minus 2z plus 5. Now we work out what factor would need to go with that z squared. So z squared minus 2z plus 5 is a factor of the equation. What would we have to multiply it by to make it back to the original equation that we had at the start, so we can find our other root? So we first of all think, what do we need to multiply z squared by to make it back to this original 2z cubed that we had? So we would need to put a 2z there. And then the second part of the bracket, what would we have to multiply 5 by to make the original minus 5 that we have in the equation there? And that, of course, would be a minus 1. So 2z minus 1 is also a factor. Now, if that's a factor, we can pull out the pieces that would have had to be multiplied together to make the cz term that we had on the left. To make z terms, we have to times the z portion in the first bracket by the number in the second, and the number in the first bracket by the z portion in the second. That's the way that we can make them. So this tells us that cz is equal to 2z plus 10z, which means that c must have been 12. For part E, we're trying to solve this equation to find out what the values of x and y would be. So what complex number needed to be on the bottom part of that first fraction to make that true? So if we're trying to isolate the x and the y, we start by putting all of the other pieces over to the right-hand side, and then put them over a common denominator of 1 plus I, so we can try and work this through to a single complex number. So if we expand that bracket, this is what we end up with, and then working that through, we get down to 4 minus I over 1 plus I. So that was equal to 1 over x plus iy. So if we flip it, then we can get x plus iy is 1 plus I over 4 minus I. And then continue through trying to make that into a single complex number, so we need to rationalize the denominator. This means we're timesing it by 4 plus I over 4 plus I, and work out what that's going to come to by completing that multiplication. We end up with 3 plus 5i over 17, and final thing to make sure we've answered the question is actually state the values of x and y from there, so pull out the real part for x and the imaginary part for y. Question 2a is a nice straightforward one, which can even be done on your graphics calculator if you know how to input things well on there. So first of all, p with that bar means it's the conjugate, so we have 3 plus I for the conjugate of p. Now work out what that would be if we minus 3 lots of q off of it. So we're just putting that into the equation, working that through, simplifying to get 9 minus 14i. For part B, we've got a complex number that's not been written in its best form. We want to turn it into a plus b root 5, so put it in the normal way that we're used to handling complex numbers. So we first of all need to rationalize the denominator. So times it by 4 plus root 5, and actually I just realized I was talking about complex numbers. This one actually isn't even a complex number, we're just working with surds and tidying it up. So then from there we multiply across the tops and the bottom, and we're working through to simplify. We get it into this form, but pay attention because the question asks for it to be a plus b root 5, not be over a fraction, so we need to turn that into rational fractions separately like this. So it's 12 over 11 and 3 over 11 root 5. For part C, we're solving this equation, which means we are finding roots of z. So if we rearrange this to be z to the power of 4 is equal to minus 16 p squared I, and picture what that looks like on the Argand diagram, it's going to be somewhere like this, because p is a real number. So we've just got a negative 16p squared in the I direction, so it will be on that I axis. Now if we are to find what z is equal to, first of all need to turn that into polar form. So we've got a magnitude of 16p squared, and the angle that we are doing there is minus pi by 2, which is this minus 90 degrees under the x-axis. But of course we could do as many circles around that axis as we wanted to. So we could add on 2k, where k is a counter, lots of pi. So 2 pi would be a full circle, and k is counting how many of those circles we have completed, which would give us an equivalent answer. So now we can use de Moivre's theorem. So z is equal to the quarter root of the modulus, and the argument then gets divided by 4 when it's in polar form, okay, because we've got that z to the power of 4. So if we tidy that up, we get the first root of z will be 2 root p to get that quarter root of 16p squared, cis minus pi by 8, where we haven't taken any extra turns around that axis yet. So the k on our first solution will just be 0, so counter being 0. So that gives us minus pi by 2 divided by 4, which gives us minus pi by 8 as the first solution. We need 4 solutions to this, because we've got z to the power of 4, so we'll have 4 roots. So the second solution is if we did our original z to the 4 if we'd taken another circle, another trip around, that would give us an equivalent. So k would be 1. And then we simplify that through. So minus pi by 2, add on 2 pi, and divide it by 4 gives us 3 pi by 8. The third one we're doing if k is equal to 2. So we've taken 2 extra turns around that Argand diagram at the beginning, and then got our third root. And the final fourth root is like this, where we have our argument is 11 pi by 8, which was taken from k being 3. So it's our original solution plus 3 extra turns around the axis. Now the issue with this final one is 11 pi by 8 actually goes over, it's a top-heavy fraction, it goes over our limit of what we state the argument as. If we go over pi, then we actually look for its equivalent by going as a negative argument instead. So that's the equivalent to minus 5 pi by 8 if we were to go under the axis and meet the same point. For part D, we've been given this complex number in a bit of an odd form, and we want to work out what we could put m as so that it would be purely real. Now, being purely real means it would have no imaginary parts. Now, at the moment, it's in too much of a mixture of things for us to be able to work out what that means. So we need to tidy this up a bit. So we work through, first of all, timesing it by the conjugate of the denominator. So we're rationalizing the denominator so that we can try to tidy this up into just one thing, or in the form of a plus bi type of complex number. So working that through looks like this, and then tidying that up we get this answer here. And then if we separate out the real and the imaginary parts, because we're trying to look at just what the imaginary part would do, and if we can eliminate that section. So we've separated the real to the left and the imaginary to the right, factorizing out that I. So from there we can see that if we put in the value of m equals 3, we would get 0 as that coefficient of I. That would eliminate the imaginary parts. We would be left with only things that were real. Now part E is quite tricky. We want to prove that this expression 1 plus z over 1 minus z is purely imaginary if we know that the modulus of z equals 1 and z is not equal to 1 itself. So we need to again be able to look at the real and imaginary parts of z. So we need to express it as x plus iy. Now, expressing it like that, let's take the other information we've been told, which is the modulus of z equals 1. So that means that x squared plus y squared is equal to 1, or x squared plus y squared equals 1 if we square both sides of that. Now take the expression of 1 plus z over 1 minus z and put in x plus iy in place of z. With that, we will then multiply by the conjugate of the bottom. Now I first of all have expressed that first fraction as pulling out the real parts and the imaginary parts just to make it super obvious with the bracketing there. So then timesing it by the conjugate would be that the iy part just becomes the plus. So if we work through multiplying that, then we get this fairly lengthy expression here. And you can just take a pause and make sure that you can do that multiplication. Then we've got a bit of multiplying out and simplifying to do. So we end up with this. Now this x squared minus y squared part, we can do something there. If we take out a factor of minus 1, we then get 1 minus x squared plus y squared. Now the reason for doing that is that we can use what we had in the question above about the modulus of z. Now it's easy to get down to this part having worked with lots of algebra and forget that you were told about the modulus of z. There must be a reason why you were told that, so let's use it here. The modulus of z gave us this expression that x squared plus y squared equals 1, so we can put that 1 in here for x squared plus y squared. What's happened so far, we've worked through, we've got the real parts to themselves, we've got the imaginary parts to themselves, we've got something on the bottom which is kind of irrelevant at the moment. It'll be a real number as it stands right now. So we would have this 1 minus 1. So that gives us nothing on that section of the fraction, and we're just left with the real half, the imaginary half of it on the right hand side. So now we've got this term here, and on the bottom 1 minus x squared is equal to y squared by rearranging what we had of x squared plus y squared equals 1. So x and y are both real numbers, so this bit down here will be a real on the denominator. Got a real coefficient there, a real y, and then we're left with an I, so there's no way that I would get multiplied out by anything else to turn it into a real number, and therefore we only have an imaginary component left. And on to question 3. So we are going to do u divided by v, where we've got these complex numbers in polar form. That's very straightforward. We just do a division of the modulus and a subtraction of the argument. Simplify that down and we get 1 over q cis 5 pi by 12. For part B, we have the real numbers, x and y are real numbers here. In this expression, find the values of x and y. I'm first of all expanding that left-hand side and set it equal to 3 minus I. Then if we pull out the real and imaginary parts to those, then we get 2x minus y are the real parts. The imaginary is x plus 2y multiplied by I. Now we can equate the real components of this. So the real parts are the 2x minus y on the left hand side, and on the right hand side it's 3, so 2x minus y must be 3. And same with the imaginary, we've got x plus 2y must be equal to minus 1. So with that real part we can rearrange this to be y equals 2x minus 3 and put it into the equation that we've got for the imaginary parts. So replace that y with 2x minus 3, so we can work that through. And we get that x equals 1. Now if x equals 1, y was 2x minus 3, so y equals minus 1. And there's your final answer. Part C is about finding x in terms of w, and we've got this expression. So we want to end up with x equals something. So let's first of all rearrange that, set these two equal to each other. Then if we square both sides, we can get rid of the square root in there. That's a bit tricky to handle. So squaring both sides gives us this. Then expand that bracket on the left-hand side. Now we want to rearrange to bring all the x's to one side and everything else to the other. So x is to the left and that 12 goes to the right. Now if we factorize out that x term, we get this line. And then we can move that 4 minus w squared over to the right hand side, and now we've got x in terms of w. Right, now part D, we've got these two complex numbers u and v, and we're told some information about the argument. So let's first of all, not just the argument, but the argument of u divided by v. So let's work out what u divided by v would look like. So this would be 1 plus pi over 5 plus 3i. Let's work that through by multiplying by the conjugate of the denominator, and we get the following when we simplify that. Okay, so expanding that multiplication, then simplifying, so we've got the real on the left and the imaginary on the right. Now the other bit of information we were told is that the argument of that number is equal to pi by 4. So if that's true, then the real and imaginary parts must be equal to each other, because an argument of pi by 4, that's 45 degrees. That gives you an isosceles triangle. So the distance on the real axis will be the same as the distance on the imaginary. So those two parts that we've got there from the expansion we did before, we can set them as being equal to each other. So if the real part equals the imaginary part, we can work through that equation, and we get down to p is equal to 4. For part E, we want to show that this equation will have two distinct real solutions. Now for that, we're always talking about the discriminant. Before we can work out the discriminant, we need to rearrange this to be something that's equal to 0. And I've factorized out the x terms as well, so we can easily pick out that coefficient of x. Now the discriminant is b squared minus 4ac. So in this case, b is 3k minus 7, a is 1, and c is k squared minus 3k, the constant at the end. So if we work through with that, we can expand out and simplify. Then we get down to this, where we've got 5k squared minus 30k plus 49. Now we need to put that into some kind of form where we know if it's always going to be positive or negative or equal to 0. So to do that, we use completing the square. So first of all, take out 5 from the k squared minus 30 bit as a factor. So you can leave the 49 alone for a second. And then we do completing the square on k squared minus 6k. So that would be k minus 3 squared minus 9 to make it equivalent. That gets times by the 5 and then added 49. Now if we tidy that up, it looks like this. And then our final thing is to write a statement about this. So because we've got that k minus 3 squared in there, we know that that will never ever be negative, because whatever k is going to get, once you've taken 3 off, it doesn't matter, you will then square it. So that will always be a positive number. If you times a positive by 5 and you add on 4, you'll still have a positive number. So for all values of k minus 3 squared will be positive. Therefore, 5 times k minus 3 squared plus 4 will be positive. This means the discriminant is always positive. And when the discriminant's positive, that means that there are 2 real roots.